In the summer of 1944, beneath the scorching Pacific sun, a 19-year-old sailor named Thomas McKenzie pressed his shoulders against the twin grips of his Oerlikon 20mm cannon aboard the U.S. Navy destroyer USS Laffey. The weapon's distinctive 60-round drum magazine gleamed above the breech, loaded with high-explosive shells that could tear through aircraft aluminum like paper. Mackenzie had no way of knowing that the cannon he operated with such deadly precision had been invented by a German engineer in the trenches of World War I, perfected by Swiss manufacturers in the mountains of Zurich, and that at this very moment Japanese naval aviators flying toward his ship were armed with nearly identical weapons based on the same revolutionary design. The morning air carried the distant drone of approaching radial engines, a sound that had become as familiar as his own heartbeat during months of kamikaze attacks off Okinawa. Through his Mark 14 gyroscopic gun sight, an electromechanical marvel developed by MIT engineers, Mackenzie tracked the incoming Japanese aircraft. The sight's internal gyroscopes automatically calculated lead angles and target trajectory, transforming the ancient art of aerial gunnery into a deadly science. What he could not see through his crosshairs was the bitter irony of the moment. The approaching Mitsubishi A6M0 fighter carried two Type 99 Mark I cannons in its wings, weapons that were licensed copies of the same Swiss Oerlikon design that had spawned his own gun. The Oerlikon 20mm cannon represented one of the most extraordinary stories of wartime weapons development, a tale that spanned 3 decades and 4 nations, each adding their own innovations to a design that would ultimately become the most prolific anti-aircraft weapon in history. More than 120,000 of these weapons would be manufactured by American factories before the war's end, while British shipyards produced another 30,000 for Royal Navy vessels. In post-war analysis conducted by the U.S. Navy Department, statisticians would determine that no fewer than 1/3 of all Japanese aircraft shot down in the Pacific theater had been destroyed by this German-invented, Swiss-perfected, American-built weapon system. The story began 30 years earlier in the mud and wire of the Western Front, where German industrialist Reinhold Becker struggled with a fundamental problem of aerial warfare. The aircraft of 1914 had been fragile constructions of canvas and wood, easily destroyed by rifle-caliber bullets. By 1918, they had evolved into more robust machines with stronger engines and better armor, requiring more powerful weapons to bring them down. Becker's solution was revolutionary: a 20mm automatic cannon that used advanced primer ignition blowback operation, firing explosive shells at 300 rounds per minute. The Becker cannon's technical innovation lay in its unusual firing sequence. Unlike conventional firearms where the bolt locks in place before firing, Becker's design fired the cartridge while the heavy bolt was still traveling forward. This meant the explosive gas pressure had to overcome the bolt's forward momentum before it could drive the mechanism backward to eject the spent case and load the next round. The result was a weapon that could handle the enormous pressures generated by 20mm explosive shells without requiring the complex locking mechanisms that made other large-caliber automatic weapons heavy and unreliable. In the bombed factories of the Ruhr Valley, German workers assembled fewer than 200 of Becker's cannons before the armistice of November 1918 brought production to a halt. The Treaty of Versailles, signed 7 months later in the Hall of Mirrors at the Palace of Versailles, contained specific clauses forbidding Germany from manufacturing or developing automatic weapons of any caliber. Article 171 stated that the manufacture or importation of arms, munitions, and war material of every kind was forbidden. For Reinhold Becker, this meant the end of his revolutionary cannon design, at least on German soil. The patents and technical drawings that Becker had developed were legally transferred to Switzerland in 1919, purchased by a small engineering firm called Seemag, Seebach Maschinenbau Aktiengesellschaft, based near Zurich. The Swiss, maintaining their traditional neutrality, saw opportunity in the world's growing demand for advanced weapons systems. Seemag's engineers, working in clean mountain factories far from the devastation of the recent war, began refining Becker's design for the rearmament period they correctly anticipated was coming. Throughout the 1920s and early 1930s, Seemag and its successor company Oerlikon Kontraves developed multiple variants of the basic design. The Oerlikon S model of 1927 improved the muzzle velocity for better armor penetration. The Oerlikon 1S of 1930 was categorized as an enhanced version with better reliability. But the real breakthrough came in 1935 with the introduction of the FF series, aircraft-mounted weapons designated with the German term Flügelfest, meaning wing-mounted and fixed. The FF family consisted of 3 main variants, each optimized for different combat roles. The FF fired a 20 by 72 mm rimmed bottleneck cartridge and weighed 24 kilograms, achieving a muzzle velocity of 550 to 600 meters per second with a cyclic rate of 520 rounds per minute. The FFL, weighing 30 kilograms, fired its projectile at 675 meters per second with a slightly slower rate of 500 rounds per minute due to its more powerful cartridge. The FFS, the heaviest at 39 kilograms, delivered the highest muzzle velocity of 830 meters per second at 470 rounds per minute. Each variant was fed from detachable drum magazines holding between 45 and 100 rounds, depending on the installation requirements. The drums themselves represented a significant engineering achievement, using spring-loaded mechanisms that could reliably feed the large 20mm cartridges, even under the extreme gravitational forces encountered during aerial combat maneuvers. In the rising militarism of the mid-1930s, the world's air forces recognized that the age of rifle-caliber aircraft armament was ending. Modern fighters were becoming larger, faster, and more heavily built, with self-sealing fuel tanks and armor plating that could absorb dozens of machine gun hits and continue flying. What was needed was a weapon that could deliver enough explosive power to destroy an aircraft with just a few well-placed shots. The Imperial Japanese Navy was among the first to recognize this reality. In 1935, Japanese naval aviation officers began a comprehensive evaluation of 20mm automatic cannons for future fighter aircraft. Their technical mission visited factories across Europe, examining weapons from multiple manufacturers before focusing on the Oerlikon family. Japanese engineers were particularly impressed by the FF and FFL variants, noting their lightweight and compact dimensions that would allow installation in the wings of the lightweight fighters they were planning. Captain Jiro Horikoshi, who would later design the famous Mitsubishi A6M0 fighter, visited the Oerlikon factory in Switzerland during 1936. He noted in his technical report that the advanced primer ignition blowback system offered significant advantages over gas-operated or recoil-operated cannon designs. The absence of complex gas systems or recoil mechanisms made the weapon inherently lighter and more compact, crucial considerations for aircraft where every kilogram of weight affected performance. Following extensive testing and evaluation, the Imperial Japanese Navy made a fateful decision in 1937 to acquire manufacturing licenses for both the FF and FFL designs. To produce these weapons domestically, a group of retired Japanese Navy admirals established the Dai Nihon Heike KK Arms Manufacturing Company. The close economic and political ties between the Navy and this new company ensured minimal competition and guaranteed production contracts. Japanese production began in 1939 with their version of the FF, initially designated Type E because the Japanese transliteration of Oerlikon was Oerlikon from late 1939 onward. The weapon was formally known as the Type 99 Mark I, with the 99 designation derived from the Japanese imperial calendar year 2599, which corresponded to 1939 in the Western calendar. The Japanese version of the FFL became the Type 99 Mark II. Interestingly, the Japanese Navy classified these 20mm weapons as machine guns rather than cannons, a bureaucratic distinction that would have important implications for crew training and tactical doctrine. Unlike the unified approach used by other nations, there was virtually no cooperation between the Japanese Army and Navy on weapons development, and these weapons were never adopted by Army aviation units. The Type 99 Mark I that entered production was optimized for the lightweight fighter aircraft philosophy that dominated Japanese naval aviation. Early models were fed from 60-round drums mounted above the weapon, though this was later increased to 100 rounds as aircraft grew larger and mission requirements demanded more ammunition capacity. The Japanese engineers made several modifications to the original Swiss design, including changes to the manufacturing tolerances to accommodate Japanese production methods and materials. While the Japanese were establishing their production lines, similar developments were occurring in Germany. The resurgent Luftwaffe had identified the need for aircraft-mounted cannon as early as 1932, when the German Air Ministry began observing French experiments with engine-mounted cannon systems. The German preference was for a powerful autocannon that could be mounted between the cylinder banks of a V-type engine and fire through the propeller hub, a configuration known as Motorkanon. However, the existing Oerlikon designs proved too large for German aircraft engines. As a compromise solution, the German company Ikaria Werke Berlin acquired licenses to produce a modified version of the Oerlikon FF, which they designated MG-FF. The MG stood for Maskengewehr, machine gun, following Luftwaffe practice of classifying weapons of 20 mm caliber and below as machine guns rather than cannons. The German MG-FF entered service in 1936 and was widely deployed on Luftwaffe aircraft by the outbreak of war in 1939. The Messerschmitt Bf 109E3, which formed the backbone of German single-seat fighter strength during the Battle of Britain in the summer of 1940, typically mounted two MG-FF cannons in the wings supplemented by two 7.92 mm MG-17 machine guns mounted on the engine cowling and synchronized to fire through the propeller disc. German engineers made one crucial improvement to the basic Oerlikon design that would prove decisive in combat. In May 1940, they introduced the MG-FF/M variant, adapted to fire a revolutionary new type of ammunition called Minengeschoss, or mine shell. These projectiles had extremely thin walls and were filled with high explosive or incendiary compounds rather than solid metal. Because the shells were lighter than conventional armor-piercing rounds, they achieved higher muzzle velocities while delivering devastating explosive effects on target. The German mine shell contained 186 grams of high-explosive filler, 3 times as much as early-model British Hispano-Suiza HS-404 cannon shells. The theory behind this innovation was that while solid bullets or armor-piercing shells had to hit vital aircraft components to be effective, an explosive shell could cause serious damage regardless of where it struck the target aircraft. Even a hit on a wingtip could start fires or cause structural damage that would bring down an enemy fighter. German test pilots who flew aircraft armed with the MG-FF/M reported that the new ammunition was devastatingly effective against British aircraft during the Battle of Britain. Flight Lieutenant Werner Molders, who would become one of Germany's leading fighter aces, noted in his combat reports that a single well-aimed burst from MG-FF/M cannons could destroy a Supermarine Spitfire or Hawker Hurricane, whereas the same target might absorb dozens of machine gun hits and continue fighting. Meanwhile, across the Atlantic, the United States Navy was struggling with its own aircraft armament problems. American naval fighters of the late 1930s were armed primarily with rifle-caliber 30-06 machine guns, adequate against the fabric-covered biplanes of World War I but increasingly ineffective against modern all-metal monoplane fighters. The Navy had experimented with 50-caliber machine guns, which offered better performance, but even these weapons lacked the hitting power needed to quickly disable enemy aircraft in the brief engagement windows typical of aerial combat. In 1935, the U.S. Navy purchased two Oerlikon 20mm Model 1934 cannons for evaluation at the Naval Proving Ground at Dahlgren, Virginia. The test results were disappointing. The weapons demonstrated low muzzle velocity and an unsatisfactory rate of fire of only 265 rounds per minute. Navy ordnance officers concluded that the Oerlikon was inadequate for American requirements and rejected the design. This decision nearly bankrupted the Swiss company, which had invested heavily in developing the American market. Ironically, it was the Imperial Japanese Navy's purchase of licensing rights that saved Oerlikon from financial ruin and allowed the company to continue development work. The Japanese orders provided crucial funding that enabled Swiss engineers to develop the improved SS variant that would later prove so successful with Allied forces. As war clouds gathered over Europe in 1940, the U.S. Navy Bureau of Ordnance began a renewed investigation into automatic weapon systems. The inadequacies of existing American aircraft armament had become apparent during the Spanish Civil War, where both German and Soviet pilots had demonstrated the superiority of cannon-armed fighters over those carrying only machine guns. Captain William H. P. Spike Blandy, the officer in charge of expediting anti-aircraft gun production within the Bureau of Ordnance, arranged for comprehensive firing tests of the latest Oerlikon variants. The weapon that arrived for testing was dramatically different from the Model 1934 that had been rejected 5 years earlier. The new Oerlikon SS incorporated all the lessons learned from combat experience in Spain and the early months of World War II. It fired a more powerful 20 by 110 mm rimmed bottleneck cartridge at 450 rounds per minute, with significantly improved muzzle velocity and reliability. Captain Blandy personally participated in the firing trials, noting the weapon's exceptional reliability under adverse conditions. The Oerlikon continued to function normally when exposed to rain, snow, and temperature extremes that would cause many other automatic weapons to jam. The gun's simple blowback operation meant there were fewer moving parts to fail, and its robust construction could absorb the shock and vibration of shipboard service without requiring constant maintenance. Most importantly for naval service, the Oerlikon required no external power source or cooling system. Unlike the complex 11-inch/75 caliber quad-mount guns that had been the Navy's primary light anti-aircraft weapon, the Oerlikon could be bolted to any available deck space and operated by a single gunner with minimal training. This flexibility was crucial for the rapid expansion of the U.S. Navy that was already beginning in anticipation of America's entry into the war. On November 9, 1940, the Bureau of Ordnance officially approved the Oerlikon for U.S. Navy service. However, acquiring the weapons proved more complicated than simply placing an order. The Swiss factory was already operating at full capacity producing weapons for Britain and other allied nations, and the German occupation of France had severed many supply routes. Moreover, American neutrality laws prohibited direct military purchases from foreign manufacturers. The solution came through a complex arrangement involving the British Purchasing Commission and the Lend-Lease Act. In May 1940, an Oerlikon engineer named Antoine Gazda arrived in New York carrying manufacturing drawings and technical specifications for the 20mm cannon. His mission was to establish American production of the Swiss weapon system to meet British requirements. The British had been seeking American manufacturing capacity since their own production facilities were inadequate to meet wartime demands. Initial negotiations centered on the America Oerlikon Gazda Corporation, a subsidiary established in Rhode Island specifically for this purpose. However, American law required that a U.S. government agency must be involved in any foreign military production contract. Captain Blandy's favorable evaluation provided the necessary justification for American involvement. The Bureau of Ordnance agreed to participate in the production program, ordering 2,500 gun assemblies under the Lend-Lease Act with 2,000 designated for British forces and 500 for American evaluation and training. To achieve the production volumes required, the Navy brought in American automotive manufacturers with experience in high-volume precision manufacturing. The Hudson Motor Car Company was selected as the primary contractor, with additional production assigned to the Pontiac Motor Division of General Motors. These companies had the industrial infrastructure and skilled workforce needed to produce the weapon in quantities that Swiss factories could never match. The transition from prototype to mass production revealed the full genius of the Oerlikon design. The weapon's simple construction made it ideal for American manufacturing methods. While early European production had been largely hand-fitted by skilled craftsmen, American factories developed assembly line techniques that could produce completed weapons at a rate of more than 1,000 units per month. The American version incorporated several improvements over the original Swiss design. U.S. Navy ordnance engineers developed a more reliable magazine system and improved the weapon's corrosion resistance for shipboard service. The distinctive 60-round drum magazine that became characteristic of U.S. Navy Oerlikon installations was an American innovation, designed to provide maximum ammunition capacity while maintaining the weapon's balance and handling characteristics. American Oerlikon production began slowly in early 1941, but rapidly accelerated as the United States moved closer to war. By December 1941, when the Japanese attack on Pearl Harbor brought America fully into the conflict, several hundred Oerlikon cannons were already installed on U.S. Navy vessels. This initial deployment proved crucial during the early months of the Pacific War, when American forces were desperately outnumbered and could not afford to waste any opportunity to destroy attacking aircraft. The first major test of American Oerlikon cannons in combat came during the Japanese attack on Pearl Harbor itself. Several U.S. Navy ships in the harbor were armed with the new weapons, and their crews had received basic training in their operation. When Japanese aircraft appeared over Pearl Harbor on the morning of December 7, 1941, Oerlikon gunners aboard ships like the USS Nevada and USS Pennsylvania engaged the attackers with devastating effect. Seaman First Class Robert Johnson, manning an Oerlikon mount aboard the USS Nevada, later described the experience in a letter to his family. When those Japanese planes came over, our new 20mm guns just tore them apart. You could see the explosive shells bursting all over their aircraft. It wasn't like the old machine guns that just punched little holes. These shells would blow big chunks right off their wings and fuselage. The effectiveness of the Oerlikon during the Pearl Harbor attack confirmed Navy confidence in the weapon system and led to accelerated production orders. By mid-1942, Oerlikon cannons were being installed on virtually every type of U.S. Navy vessel, from small PT boats to massive aircraft carriers. The weapon's versatility allowed it to be mounted in single, twin, or even quadruple configurations depending on the available deck space and specific mission requirements. Training American sailors to operate the Oerlikon effectively required developing new gunnery techniques optimized for the weapon's characteristics. The 20mm explosive shells followed a different ballistic trajectory than the 50 caliber bullets that gunners were familiar with, requiring adjustments to aiming methods and lead calculations. Navy gunnery schools established specialized Oerlikon training programs that taught sailors to engage fast-moving aircraft at ranges up to 1,200 yards. The key to effective Oerlikon gunnery lay in understanding the weapon's ballistic limitations and advantages. The relatively heavy 20mm projectile had a lower muzzle velocity than rifle-caliber bullets, meaning that gunners had to lead their targets by greater distances at longer ranges. However, the explosive warheads meant that near misses could still damage or disable enemy aircraft through fragmentation effects. Navy training manuals emphasized that Oerlikon gunners should open fire at maximum effective range and continue shooting until the target was either destroyed or had passed beyond engagement distance. The 60-round magazine provided enough ammunition for sustained engagement, but gunners had to be trained to change magazines quickly during lulls in combat action. The most significant advancement in American Oerlikon effectiveness came with the introduction of the Mark 14 gyroscopic gun sight in 1943. This electromechanical marvel, developed by MIT engineers, represented one of the most sophisticated fire control systems of World War II. The sight used internal gyroscopes to automatically calculate target lead angles, compensating for the movement of both the firing ship and the target aircraft. The Mark 14 sight transformed Oerlikon gunnery from an art based on experience and intuition into a precise science. Gunners no longer had to estimate lead angles based on visual assessment of target speed and direction. Instead, they simply placed the sight's illuminated reticle on the target aircraft and pulled the trigger. The gyroscopes automatically adjusted the aiming point to compensate for the ballistic characteristics of the 20mm projectile and the relative motion of ship and aircraft. Combat effectiveness studies conducted after the war showed that Oerlikon installations equipped with Mark 14 sights achieved hit rates more than 3 times higher than those using simple ring and post sights. This improvement was crucial during the intensifying air attacks of 1943 and 1944, when Japanese forces began employing more sophisticated tactics and aircraft specifically designed to penetrate American naval defenses. The ultimate test of American Oerlikon effectiveness came during the kamikaze attacks that began in earnest during the October 1944 Battle of Leyte Gulf. Japanese commanders, recognizing that conventional air attacks were becoming increasingly ineffective against heavily defended American naval formations, adopted suicide tactics that guaranteed target destruction if the attacking aircraft could reach its objective. Kamikaze attacks presented a unique challenge for anti-aircraft gunners. Unlike conventional bombing or torpedo attacks, where aircraft attempted to release their weapons and escape, kamikaze pilots were committed to pressing their attacks regardless of defensive fire. This meant that even heavily damaged aircraft might continue their attack runs, requiring defensive weapons that could deliver instant, catastrophic damage to stop an incoming suicide plane. The Oerlikon's explosive 20mm shells proved ideally suited to this type of engagement. A single hit from an Oerlikon projectile could sever control cables, destroy engine components, or cause structural failures that would send a kamikaze aircraft plummeting into the sea short of its target. Unlike machine gun bullets that might wound a pilot without immediately disabling his aircraft, Oerlikon shells could destroy the aircraft itself in a single hit. During the Battle of Okinawa in spring 1945, American Oerlikon gunners faced the most intensive kamikaze campaign of the war. Japanese commanders launched 10 major suicide attacks, designated Kikusui operations, between April and June 1945. These attacks involved thousands of aircraft, both conventional bombers and fighters converted for suicide missions, attacking American naval forces supporting the invasion. The radar picket destroyers stationed at the outer edge of the American formation bore the brunt of these attacks. Ships like the USS Laffey, USS Aaron Ward, and USS Hugh W. Hadley faced dozens of kamikaze aircraft in single engagements, their survival depending entirely on the effectiveness of their anti-aircraft armament. The USS Laffey's action on April 16, 1945, became legendary among naval historians as an example of defensive gunnery at its finest. During an 80-minute period, the destroyer's crew fought off attacks by more than 20 kamikaze aircraft. The ship's 6 Oerlikon cannons, manned by sailors like Thomas McKenzie, accounted for the destruction of multiple attacking aircraft. McKenzie himself was credited with shooting down 3 kamikaze planes, using his Mark 14 sight to track the diving aircraft and deliver precise bursts of 20mm explosive shells. In his post-action report, McKenzie described the experience. "You could see those Jap planes coming in from all directions, some diving straight down, others coming in low over the water. The 20mm was perfect for this kind of fighting, fast enough to track the targets and powerful enough to blow them apart with just a few hits. When you hit one of those planes with a 20mm shell, you knew it, there would be a big flash and pieces would start flying off." The statistics compiled by the U.S. Navy after the Okinawa campaign confirmed the Oerlikon's crucial role in defending American naval forces. Of the nearly 2,000 Japanese aircraft destroyed during the campaign, more than 600 were credited to 20mm Oerlikon cannons. This represented approximately 30% of all aerial victories, making the Oerlikon the single most effective anti-aircraft weapon system in the American inventory. However, the same battles that demonstrated the Oerlikon's effectiveness also revealed its limitations. As Japanese kamikaze attacks intensified, Navy commanders discovered that 20mm explosive shells, while deadly against conventional aircraft, sometimes lacked the stopping power needed to immediately disable large, heavily built bombers converted for suicide missions. Aircraft like the twin-engine Mitsubishi G4M Betty bomber could absorb multiple 20mm hits and continue their attack runs until they struck their targets. This limitation led to the increasing deployment of 40mm Bofors cannons as the primary anti-aircraft armament on major U.S. Navy vessels. The Swedish-designed Bofors fired a shell twice the weight of the Oerlikon projectile, with correspondingly greater destructive power against large aircraft. However, the Bofors was also much heavier, required a larger crew, and could not be installed in the confined spaces where Oerlikon cannons operated effectively. The result was a complementary weapons system that maximized defensive coverage. Bofors cannons provided long-range interception capability against large formations of attacking aircraft, while Oerlikon cannons served as the final defensive barrier against individual aircraft that penetrated the outer defense zones. This layered approach proved devastatingly effective during the final months of the Pacific War. Throughout this period, one of the war's strangest ironies continued to play out in Pacific skies. While American sailors like Thomas McKenzie used Oerlikon cannons to destroy Japanese aircraft, many of those same Japanese aircraft were armed with Type 99 cannons that were themselves derived from the same Swiss Oerlikon design. Japanese and American pilots were literally shooting at each other with weapons based on identical engineering principles, manufactured under licenses acquired from the same Swiss company. This situation created what American pilots called Twilight Zone scenarios during aerial combat. Lieutenant Commander Edward Butch O'Hare, who would become the Navy's first fighter ace of World War II, described engaging a formation of Japanese Mitsubishi A6M0 fighters over Wake Island in early 1942. "It was the strangest thing here. We were, both sides using guns that were basically the same design, trying to kill each other. Our 20mm cannons were firing at their Zeros, and their 20mm cannons were firing back at us. The whole thing seemed crazy when you stopped to think about it." The Japanese perspective on this weapon symmetry was quite different. Imperial Japanese Navy pilots generally viewed their Type 99 cannons as adequate but not exceptional weapons. The lightweight construction that made them suitable for installation in Japanese fighters also limited their effectiveness compared to heavier cannon designs used by other nations. Japanese Navy pilot Saburo Sakai, who flew Mitsubishi A6M0 fighters throughout much of the Pacific War, noted in his memoirs that the Type 99 Mark I cannon required precise aiming to be effective. The 20mm cannon was useful against American bombers, but you had to get close and hit vital areas to bring them down quickly. Against fighters, it was better to use the machine guns for most of your firing and save the cannon shells for the killing shot. The limited ammunition capacity of Japanese installations compounded this problem. While American naval Oerlikon mounts carried 60 rounds per gun and could be quickly reloaded during combat, Japanese aircraft installations typically carried only 100 rounds total per cannon and could not be reloaded in flight. This forced Japanese pilots to be extremely conservative with their cannon ammunition, often saving it for the most favorable shooting opportunities. Japanese aircraft maintenance crews also struggled with the complexity of the Type 99 system compared to the simpler machine gun installations they were familiar with. The drum feed mechanisms were prone to jamming if not properly maintained, and the explosive shells required more careful handling than conventional ammunition. As the war progressed and Japanese logistical systems became increasingly strained, these maintenance issues became more serious problems. Despite these limitations, Japanese engineers continued to refine the Type 99 design throughout the war. The Type 99 Mark II, based on the heavier Oerlikon FFL, offered improved ballistic performance but at the cost of additional weight and complexity. Late war variants incorporated belt feed systems similar to those used on American installations, increasing ammunition capacity to 125 rounds per gun. However, these improvements came too late to significantly affect Japanese combat effectiveness. By 1944, when the most advanced Type 99 variants were entering service, Japanese industry was already struggling with critical shortages of raw materials and skilled workers. Many aircraft were delivered with simplified armament installations, and pilot training had been abbreviated to the point where few aviators could effectively employ the sophisticated weapon systems available to them. The Italian perspective on Oerlikon-derived weapons was equally complex but reflected different strategic priorities and industrial constraints. Italian aircraft designers had recognized the need for effective cannon armament as early as the mid-1930s, but the country's limited industrial base made it difficult to develop indigenous weapon systems that could compete with foreign designs. Italy's Regia Aeronautica initially relied on rifle-caliber machine guns for fighter armament, a decision that proved increasingly inadequate as the war progressed. The Macchi C-200 Setta, which was Italy's primary fighter aircraft at the time of their entry into World War II, was armed only with two 12.7mm Breda Safet machine guns. While these weapons were reliable and well-manufactured, they lacked the hitting power needed to quickly destroy modern all-metal aircraft. Italian engineers at companies like Macchi Aeronautica and Fiat recognized that cannon armament was essential for competitive fighter aircraft. However, developing indigenous 20mm weapons proved challenging due to limited resources and the urgency of wartime production schedules. The solution was to acquire manufacturing licenses for proven foreign designs, specifically the German MG-151/20 cannon system. The MG-151/20 represented an evolution of the original Oerlikon concept, incorporating improvements developed by German engineers during the early war years. Unlike the simple blowback operation of the original Oerlikon design, the MG-151/20 used a more sophisticated recoil operation with a locked breech, allowing it to fire more powerful ammunition at higher muzzle velocities. Italian production of the MG-151/20 began in 1942. Initially at Fiat facilities in Turin. The weapon was installed on advanced Italian fighter aircraft like the Macchi C-205 Veltro, Fiat G55 Centauro, and Region Re 2005 Sagittario. These aircraft, powered by license-built German Daimler-Benz engines and armed with German-derived cannon, represented the pinnacle of Italian fighter development. The Macchi C-205 Veltro, in particular, demonstrated the effectiveness of combining Italian aerodynamic design with German engine and armament technology. The aircraft was typically armed with two 12.7mm Breda Safet machine guns mounted in the engine cowling and two 20mm MG-151/20 cannons installed in the wings. This armament package provided both the rapid fire capability needed for deflection shooting and the destructive power required to disable heavily built enemy aircraft. Italian pilots who flew these advanced fighters praised their effectiveness in combat against Allied aircraft. Maggiore Adriano Visconti, one of Italy's leading fighter aces, noted in his combat reports that the MG-151/20 cannons were devastatingly effective against American heavy bombers. A few well-placed 20mm shells could set fire to a B-24 or cause structural damage that would force it out of formation. The cannon gave us the ability to engage the American bombers on equal terms, something that had been impossible with machine gun armament alone. However, Italian production of advanced fighters and their associated weapon systems remained limited throughout the war. Industrial capacity that might have been devoted to aircraft manufacturing was diverted to other military requirements, and chronic shortages of strategic materials limited production runs. Only two 62 Macchi C-205 aircraft were completed before Italy's armistice with the Allies in September 1943, far fewer than needed to significantly impact the air war. The armistice itself created additional complications for Italian forces equipped with advanced weapons systems. Some units continued fighting alongside German forces as part of the Italian Social Republic, while others joined the Allied-aligned Italian co-belligerent air force. This division meant that Italian pilots found themselves on both sides of the conflict, sometimes engaging each other with identical aircraft and weapons. The post-armistice period also saw the German seizure of Italian aircraft production facilities and weapon stockpiles. Many Italian-built fighters were impressed into Luftwaffe service, while manufacturing equipment was relocated to German factories to support continued production. This transfer represented a significant loss of Italian industrial capability and technical expertise. Meanwhile, the global success of Oerlikon-derived weapons had attracted the attention of military planners worldwide. By 1943, variants of the basic Swiss design were in production in more than a dozen countries, each adapted to local requirements and manufacturing capabilities. The Soviet Union produced the SHVAK cannon based on Hispano-Suiza developments of the Oerlikon concept. Britain manufactured both the original Oerlikon design and the more advanced Hispano-Suiza HS-404. Even neutral countries like Sweden and Switzerland continued producing weapons for export to various combatants. This proliferation of Oerlikon-derived weapons created a complex web of technological transfer and competitive development. Engineers in each producing country made incremental improvements to address specific operational requirements or manufacturing constraints. The result was a family of related weapons that shared basic operating principles but differed significantly in detailed design and performance characteristics. The cumulative effect of these developments was to establish 20mm cannon as the standard aircraft armament for the remainder of World War II and beyond. By 1944, virtually every major combatant was producing aircraft armed with 20mm weapons based on the original Oerlikon concept. The age of rifle-caliber aircraft armament was definitively over, replaced by explosive cannon shells that could disable enemy aircraft with a single well-placed hit. American production of Oerlikon cannons reached its peak in 1944, when factories were completing more than 2,000 weapons per month. The Hudson Motor Car Company alone was producing 1,200 Oerlikon cannons monthly, while General Motors facilities added another 800 units to monthly output. This production rate meant that new U.S. Navy vessels could be equipped with their full armament complement immediately upon completion, without the delays that had plagued earlier construction programs. The logistics of supporting this massive Oerlikon fleet required equally impressive achievements in ammunition production. Each 20mm round consisted of a brass cartridge case, explosive warhead, fusing system, and propellant charge, all of which had to be manufactured to precise tolerances to ensure reliable weapon function. American ammunition plants produced more than 500 million rounds of 20mm ammunition during World War II, enough to supply every Oerlikon installation throughout the conflict. Quality control for both weapons and ammunition became a critical factor as production volumes increased. Early production runs occasionally suffered from manufacturing defects that could cause weapon malfunctions during combat engagements. The Navy established comprehensive testing programs that subjected sample weapons from each production batch to extensive firing trials before approving them for fleet service. These testing programs revealed the remarkable durability of the Oerlikon design under combat conditions. Test weapons were subjected to firing cycles that simulated months of combat use, exposed to salt water and extreme temperatures that duplicated shipboard service conditions, and deliberately abused to determine their failure modes. The results consistently confirmed that properly manufactured Oerlikon cannons could withstand treatment that would disable more complex weapon systems. The simplicity that made the Oerlikon so reliable also made it relatively easy to maintain under combat conditions. Navy armorers' mates could completely disassemble and reassemble an Oerlikon cannon using only basic hand tools, a crucial advantage when sophisticated maintenance facilities were unavailable. This maintenance simplicity was particularly valuable during extended operations in the Pacific, where naval task forces operated thousands of miles from major repair bases. Combat experience also revealed the psychological impact of effective anti-aircraft weapons on both friendly and enemy personnel. American sailors manning Oerlikon installations reported high levels of confidence in their ability to defend their ships against air attack. This confidence translated into improved overall combat effectiveness, as crews could focus on their primary missions rather than worrying about defensive vulnerabilities. Conversely, Japanese pilots increasingly reported that heavily armed American ships were extremely dangerous targets that required careful approach and tactical coordination to attack successfully. The concentration of defensive firepower represented by multiple Oerlikon installations, coordinated by radar and sophisticated fire control systems, created defensive zones that were difficult for even experienced pilots to penetrate. The statistical analysis conducted by the U.S. Navy after the war confirmed the Oerlikon's central role in American defensive success. Between December 1941 and September 1944, U.S. Navy Oerlikon cannons were credited with destroying 32% of all Japanese aircraft shot down in the Pacific theater. This figure represented more than 3,000 individual aircraft destroyed by Oerlikon fire, making it the single most successful anti-aircraft weapon system in American service. These statistics become even more remarkable when considered in the context of the overall Pacific Air War. Japanese naval and army air forces began the war with approximately 10,000 aircraft of all types. By September 1944, when the Oerlikon effectiveness study was conducted, Japanese air strength had been reduced to fewer than 2,000 operational aircraft despite continuous production throughout the war period. The American Oerlikon contribution to this attrition represented a significant strategic achievement that extended far beyond simple defensive success. Each Japanese aircraft destroyed by anti-aircraft fire represented not only the loss of the aircraft itself but also the trained aircrew, whose replacement became increasingly difficult as the war progressed and Japanese training programs were abbreviated due to fuel and equipment shortages. Moreover, the threat posed by effective American anti-aircraft defenses forced Japanese commanders to modify their tactical approaches in ways that reduced overall mission effectiveness. Japanese aircraft were compelled to attack from higher altitudes and greater distances to avoid defensive fire, reducing bombing accuracy and increasing fuel consumption. Fighter escorts had to be allocated to suppress anti-aircraft positions rather than engaging American interceptor aircraft, diluting the effectiveness of Japanese offensive operations. The cumulative effect of these factors was to accelerate the decline of Japanese air power throughout 1943 and 1944, contributing to American air superiority that became decisive during the final phases of the Pacific Campaign. While other factors certainly contributed to this outcome, including the increasing qualitative and quantitative superiority of American aircraft and the attrition of experienced Japanese pilots, the effectiveness of American anti-aircraft defenses played a crucial role in the overall strategic equation. The technological lessons learned from Oerlikon development and deployment would influence post-war military aviation for decades. The basic principle that aircraft armament required explosive projectiles to be effective against modern aircraft became universal doctrine that guided weapons development well into the jet age. Even today, most military aircraft are armed with cannon systems that can trace their conceptual ancestry to the innovations pioneered by Reinhold Becker in the trenches of World War I. However, the end of World War II also marked the beginning of the end for the Oerlikon as a frontline weapons system. The advent of jet aircraft with much higher speeds and operating altitudes made manual tracking and aiming increasingly difficult. The development of guided missiles provided defensive capabilities that far exceeded those of conventional anti-aircraft guns. By the early 1950s, most major navies were beginning to phase out their Oerlikon installations in favor of more advanced weapons systems. The final chapter of the Oerlikon's wartime service came during the Korean War, when many World War II vintage installations saw combat for the last time. American destroyers and cruisers operating in Korean waters used their 20mm cannons to provide close-range defense against North Korean aircraft, and to support amphibious operations with direct fire against shore targets. These final combat applications demonstrated both the continuing utility and the ultimate limitations of the Oerlikon concept. Against the relatively primitive aircraft employed by North Korean forces, the 20mm cannons remained effective defensive weapons. However, when confronted by modern jet fighters like the Soviet-supplied MiG-15, the manual tracking and aiming systems that had been adequate against propeller-driven aircraft proved completely inadequate. By 1955, the U.S. Navy had removed most Oerlikon installations from active service, retaining only a few weapons for use against small surface targets like patrol boats or swimmer delivery vehicles. The British Royal Navy followed a similar timeline, gradually replacing Oerlikon mountings with more modern weapon systems throughout the 1950s and early 1960s. Today, more than 75 years after the first Oerlikon cannons entered American service, examples of these weapons can be found in maritime museums around the world. Preserved aboard museum ships like the USS Massachusetts, USS Alabama, and USS Intrepid, these cannons serve as reminders of the crucial role they played in the Pacific victory. Veterans who manned these weapons during World War II, now in their 90s, still gather occasionally at reunions to share memories of the desperate battles where their accurate gunnery made the difference between survival and destruction. Their stories preserve the human dimension of what was ultimately a triumph of industrial engineering and manufacturing capability applied to the ancient art of warfare. The legacy of the Oerlikon extends beyond its direct military applications to encompass broader lessons about international technology transfer, industrial mobilization, and the rapid evolution of military technology under wartime pressures. The weapons development demonstrated how innovations created in one country could be refined and improved by engineers working in different nations and industrial systems, ultimately producing results that exceeded what any single country could have achieved working alone. Perhaps most importantly, the Oerlikon story illustrates the crucial importance of defensive weapons systems in modern warfare. While offensive capabilities often receive more attention in military histories, the ability to defend against enemy attacks proved equally decisive in determining the war's outcome. The thousands of American sailors who served Oerlikon cannons contributed as directly to ultimate victory as the pilots who flew the combat missions that captured public attention. In the summer of 1944, as Thomas McKenzie tracked another formation of Japanese aircraft approaching his destroyer, he represented the culmination of a technological and strategic evolution that had begun 30 years earlier in a German engineer's workshop. The weapon he operated with such deadly effectiveness embodied the contributions of designers, engineers, and workers from 4 different countries, united by the common goal of creating the most effective anti-aircraft system possible. When McKenzie pressed his trigger and sent a stream of 20mm explosive shells toward the approaching kamikaze aircraft, he was writing the final chapter of one of World War II's most remarkable technological success stories. The German invented, Swiss perfected, American-built weapon that had downed 1/3 of all Japanese aircraft destroyed in the Pacific War was about to claim another victory in the long struggle for control of Pacific skies. The irony that Japanese aircraft armed with weapons based on the same technological foundation were simultaneously attacking his ship would have been lost on McKenzie in the heat of combat. But that irony perfectly captured the complex international heritage of the weapon that had become America's most effective defense against the very enemy that had helped save its original manufacturer from bankruptcy 15 years earlier. In the end, the story of the Oerlikon 20mm cannon is not simply the story of a weapon, but the story of how innovative engineering, international cooperation, and industrial determination combined to create one of the most successful military technologies in history. From the mud of World War I battlefields to the Pacific campaigns that ended World War II, the Oerlikon served as a testament to human ingenuity applied to the fundamental challenge of survival in warfare.